Hey everyone, in this video we are going to discuss the concept of equality of sets, which is actually a relation on a collection of sets. So without any further delay, let's see what does it mean for two sets to be equal. I mean, what is the definition of equality of two sets? If I have two sets A and B, I will say that those two sets A and B are equal, and I denote this fact of being equal by this notation. And we read this symbol as A is equal to B if this thing happens. What? A is equal to B if A and B have the same elements. Now, I call this very definition as the informal or layman definition. Why? This definition itself raises several questions. What do we precisely mean by the word same? Now, if you are asking such a question, it means that you are more rigorous. And obviously, this definition lacks precision. So, how can we make this word same more precise? Is it a brand new concept in set theory, the concept of same, or is it just a shorthand notation to denote something which we already know? So, once we ask this question, it means that we are trying to formalize the concept of same. So, how do mathematicians or set theorists actually define the concept of equality of two sets? Here we see how mathematicians define the equality of two sets. What mathematicians do? Mathematicians use the concept of belonging or the concept of membership to explain the concept of equality. Now, you should note here one thing, that in complete axiomatic approaches to set theory, the concept of membership or the concept of belonging is actually a primitive concept. So, I am assuming that you have at least intuitive feeling of what does it mean for an element to belong to another set. So, I am assuming that you are comfortable with this symbol. Now, how mathematicians define the concept of equality of two sets in terms of the concept of belonging? Here it is. If A and B are two sets, the set A is equal to the set B if and only if this thing happens. What? X belongs to B if X belongs to A. Remember that for all X belonging to A. What does this thing tells me? This part of this condition tells me, this part tells me that every element of A must be an element of B. Now, is this enough? Obviously not. This is not enough. For two sets to be equal, besides satisfying this very condition, those two sets must also satisfy this very condition. Means that for two sets to be equal to each other, they must satisfy these two pieces of information simultaneously. X belongs to A for all X belonging to A, and X belongs to A if X belongs to B, but this should happen for every X in B. So, in simple words, I will say that, or a mathematician will say that a set A is equal to the set B if every element of A is present in the set B. Also, every element of B is present in the set A. So, this is the formal version of the definition of equality of two sets. The concept of same is not a new concept in set theory. Instead, it is just a short version or shortcut to say all these things. Same means this very thing. Whenever you hear or read the word same in the definition of sets, you should immediately imply this very thing. And whenever you have this very thing, you can use, instead of saying all these two lines mouthfully, it is convenient to say shortcut same. simply same means this thing and this thing back means this thing. It means that if someone defines the equality of two sets as two sets are equal if they have the same elements, actually by same he means this very thing. So this is the definition of equality of two sets. You should note one more thing here, that in axiomatic approaches to set theory, this definition is actually an axiom and has a special name, the axiom of extensionality. In naive approach to set theory, we implicitly describe the axiom of extensionality under the definition of equality of two sets. What is the relation between set equality and set inclusion? Don't worry, set inclusion is nothing but another name for the concept of subset. Now, by definition, set A is equal to the set B if and only if this thing happens. Now, if you observe, this thing tells me that every element of A is also an element of B. In other words, every element which is present in the set A is also present in the set B. Now, if you recall the definition of subset, this coincides, this condition coincides with the definition of subset. So this is nothing but this notation. So every element of A is also an element of B. It means that A is the subset of B, and every element of B is also an element of A. It means that B is subset of A. So I can rephrase this definition in a different terminology in the terms of subset notation, and here it is. We can equivalently write this definition of equality of two sets this way: A, which is a set, is equal to the set B if and only if A is the subset of B. You should note here, this is symbolic way to represent and B is subset of A. Now, this is a compound statement and it includes and, not or. Means that for this whole compound statement to be true, both of these individual components must be true. So for this whole statement to be true, these individual statements must also be true. So logically, it means that two sets are equal. If I have two sets A and B, they are equal if they are subsets of each other. Now, we have a thumb rule to show that precisely how two sets are equal. This is the thumb rule. Now, the concept of same was quite vague for us. Now we have a precise definition of equality of sets. Now, using that definition, I can use it as a thumb rule to show that given two sets are equal. Now, if I have two sets A and B, what is it that is sufficient to say that these two sets A and B are equal? To show that A and B are equal, you just have to show that one is the subset of another. That is, in order to show that two sets A and B are equal, you just have to show that A is the subset of B and B is the subset of A. Now, I have a question. When two sets are not equal? Now, asking this question, you are simply asking that when this statement is not true. Now, according to logic, this statement is not true only if one of the individual components of the statement is true and the other is false. So, if you are asking when two sets are not equal, it means that you have to negate this very thing. So, A and B are equal if A is subset of B and B is subset of A. It means that if A is subset of B and B is not subset of A, this statement will not hold. So to show that two sets are not equal, you just have to show that at least A is not subset of B or B is not subset of A. It is also possible that A is not subset of B and B is also not subset of B. In that case also A is not equal to B. So what is it that is a minimum requirement to show that two sets are not equal? The minimum requirement is that show that one of the sets is not the subset of another. Here are few examples to brush our teeth. In my first example, I have two sets A and B, and set A consists of these three elements and set B consists of these three elements. And now I want to know whether these two sets A and B are equal or not. So let's apply the definition of equality to this example. Now, I know A is equal to B if A is subset of A and B is subset of A. So, is A subset of B? Obviously, A is subset of B. Is B subset of A? As you can see, obviously B is also subset of A. So these two sets satisfy the both conditions for two sets to be equal. So by definition, these two sets are equal. Now you should note here one thing, and that is the elements of this set are ordered in a different way as that of the elements of this very set. So this example indicates the fact that you can have two sets which are equal in spite of the fact that their elements are not ordered in the same way. So for two sets to be equal, order of elements is not important. This is my second example, and this is the roster form of these two sets. As you can see, I want to know whether A is equal to B or not, and I know by definition A is equal to B if and only if every element of A is present in the set B and every element of the set B is also present in the set A. So, is every element of the set A present in the set B? Obviously, as you can see, every element of A is present in the set B. And also, is every element of B present in the set A? Obviously, as you can see yourself, every element of B is also present in the set A. Means that A is subset of B and B is subset of A. So by definition, A is equal to B. Now, here in this example, you should note one more thing. As you can see, -9 and +5 are repeated in this set twice. But still, according to definition, these two sets turn out to be equal. So this example indicates the fact that repetition of an element is not allowed in a set. In other words, if an element in a set is repeated, that makes no difference. That makes totally no difference. That is what it is. I would like to remark here, that is, order of elements in a set does not matter by definition of equality of two sets, and repetition of an element in a set is not allowed or does not make any difference in a set is also a logical implication of the equality of two sets or the axiom of extensionality. Here is another example, and this example will indicate the fact that a set is not changed if it is described differently. Here I have three sets A, B, and C, and as you can see, my first set has element 3, the only element, and my set B consists of the solutions to this very equation, and the set C consists of those natural numbers satisfying this property. Now, clearly these three sets are described differently, but the question is the set A equal to the set B? According to the definition of equality, axiom of extensionality, these two sets are equal. So the purpose of this very example was to highlight the fact that if a set is described in different ways, it does not change the set. Actually, a set is not determined by its description, but by its elements. That is what the axiom of extensionality says. It says us that a set is determined by its elements. Thanks a lot.